let's see here. Joel, one of your lab mates, has granted me permission to work with him on the data, and then follow this pattern if you have any questions. And also, you can feel free to email me with any questions if you're still stuck on something. All right, if you will, let's go back to. Can you take us over first to the rubric? So for your graphs, you have three graphs there: linear speed versus time, which is really your calibration graphs. And then F versus A, that's force equals force versus acceleration. We're going to see that the relationship between those, the slope of that, has the mass that we're expecting for the whole system to move. And then A versus 1 over M, that's the one where we see that acceleration is equal, inversely proportional to the mass, and that the slope of that graph will be the total force that's causing the system to accelerate for part C. So everything else in here, just make sure that you have all those things. Make sure that your labels are figure 1 in the, figure 2 is those are the Arabic numbers. And then for the tables down at the bottom, these are not going to be tables of the data. They're not going to be tables of the data that is used to the mass and acceleration data to construct the part B and C graphs. These tables are only to take the slopes of those graphs and compare them to something that we know we expect it to be, which is your mass for part B and mass of the system for part B, and the difference of the masses, or 10 grams, for part C. Does that help?
Yeah, that makes sense.
All right. Now, just a little reminder for everybody who's listening to this is, number one, make sure that you italicize all variables. You now know how to do that. If you don't know how to use subscripts and superscripts, please reach out to me. Let me know. Let's get this skill under your belt. Make sure that you're using the proper capitalization for variables. Nearly everything that we've worked with so far, except for force, has been lowercase. Make sure that you move objects around after you've got content in there, so that you can get the best looking appearance of your writing. When you get to results section, put your stuff in place there and then start talking about what you see there. That will help you get things to talk about for when you're in your analysis section. If there's a data point that's errant, if there's something else, bring those into consideration. In this case, as you'll see, he's got an extra data point that is pulling up and increasing the slope and should not be included in the analysis, because it can be easily demonstrated that that is giving a wrong, much more incorrect representation of the experiment. So make sure that, in your case, that you say we have 6 data points, we only use the first 5, because the sixth one is clearly pulling it up by multiple grams. So there's that. And then you just talk about it. Use the percent difference, percent error, rather, as you're talking about stuff. Use the fact that you're looking at equations 2, 4, 8, or 9, and you're using that as your frame of reference to make these graphs and get these extractions, so that you're justifying. You're not just saying, well, everything looks good, but you're saying it's good. We can tell because it is a linear fit. It is an inverse law fit, and so on. And if you want to send it to me just to kind of see how things look when you're close to Tuesdays, shoot me an email and I'll take a look at that. Okay, so Joel, you've got data here for part B and part C. You already have your data for part A. Is that correct?
Uh, yes, it's right here.
Okay. Why don't you go ahead and highlight, just highlight A, B, C, and D, those 4 columns. We're going to insert a table that has all this. This is kind of a quick and dirty way to do it. Click on the charts. Yep, just click on that. Go to the dots one only. Okay, so we've got 2, 3 data sets here. One of those is run 9, so you can click on the orange one and delete that. That's just time versus time. Like I said, this is a quick and dirty way to do this. Okay, and then right click and select data. And then go to run number 9 and edit. All right, we're going to change that from column A, those A's, to C's. So just click on the A and delete, and do the same thing with the first one. Otherwise, we have to go through 84 cells to get it captured. then drop that down, and OK, and then OK again. All right, there's your two data sets. Click over here on the left-hand side where it says 1. We want to rescale that. Yeah, right-click and then scale or format axis.
Axis.
And we're going to change that maximum from 7 to 1. And just hit tab to skip out of there or something. I click elsewhere, one of those two. There you go. Okay, so run 6 is the blue dots. Those have a slope. Run 7, run 9 has fairly horizontal. So your data is pretty good set there. Okay, so about 2 seconds is a good start. And that goes, so for the blue, you see how it starts at 2 seconds? Well, it's already in the constant acceleration during that time. So from about 2 seconds to about 3.5 seconds, it looks like it's in a pretty constant acceleration.
Yeah.
So let's go to your data. And since this is a copy of your original data, we're just going to delete stuff. So go over to column A and B and just highlight everything that's below 2 seconds. So you're going to go from about A2 to B10. And just hit delete. And then scroll down and start from about 3.5 seconds and delete the rest of the data in that range. All right, so you can jump back up to the top. And now your graph is only the data that during an acceleration. We've just gotten rid of the stuff that we're not going to need. We're not doing deep analysis with this. We're demonstrating that the acceleration was reduced by adding that calibrating mass. And then you can do the same thing here. Look at that. That's just like a couple data points, 1 and 2. So just delete those first 2 data points for run 9. Go ahead. There you go. Okay, so now go up to, so click on your graph somewhere, anywhere in your graph. All right, now that we know how to put things on there, go up to chart design up at the top of your screen. And go over to the left where you see quick layout. And your 9th tile there has a little F sub X in there. That's gonna put everything in place and fit trend lines on there. So you can click on and delete your legend. That is stretching out somewhere and saying something is somewhere. When you have an X value and no Y value, then Excel counts that as a data that has no value for the Y axis. And so it plots it. And you can tell that because the default setting for a trend line is to go from the first to the last data point over that range only until you extend it on your own. Okay, so move your slopes or move your fit trend lines. You can come back and fix this graph later with all the bells and whistles that it needs, including just click on the equations. Click and drag. Make it easy to see. There we go. That one's good. And now you can see you went from 0.11 to negative 0.11 to negative 0.01. So you had 3 grams as your calibration mass?
Yes.
Okay, put that somewhere in the space just below your graph, just kind of down there. Calibration mass 3 grams. Now it does not surprise me that amount. So so there's that. Okay, next. So this looks good. Go ahead and hit save, and then let's move over to the other thing. Okay, so looking at this, you have 105, 95, and so on and so forth. Okay, so next, your numbers look really good for your first graph. Your second graph, we got a little bit of a thing over there in your inverse mass. Let's take a quick glance at that and get, so highlight just the numbers 5 through 3.125. Go up to the top. You got 2 options there for truncating things. It's under right where it says general, and then you got $ and stuff like that. You have those 2 options. If you do the one on the right, it'll shorten the number of decimal places. But anyways, now you can hit that right hand facing dot to shorten your decimal places to a more manageable number. We don't need 3 decimal places. Bingo, you're good to go. When you copy and paste that into Word, make sure that those zeros after the 5 stick around. Okay, so now your your tables are ready for graphing. Let's go ahead and go back to part B over here on the left side. and highlight Y versus X. So highlight the force data. And then insert XY chart. What this did is it automatically, and if you do this, it always puts it as the Y values because X can be just the number of cells. It's a default thing. So now we can click on the X range and add the accelerations as your slope, or accelerations as your X values. Yep. All right. There we go. Click OK. Okay, again. Okay, so looking at this data, you can clearly see that there's already one out of alignment.
Mhm.
And that one may play a factor when we're looking at part C as well. But let's go ahead and go up to the quick layout and let's throw on the FX tile option. That gives us all our bells and whistles and our fit trend line. Get rid of your legend so we can fill up the space. All right, so interesting. Oh, let's go back up to your formulas and check and see, because I saw those negative signs, but my brain didn't quite register that it was off. Go back up to E4 if you would. E4 there. All right, that's C4 minus B4. So you got actually M2 minus M1. It should be M1 minus M2. Enter. Yep, well, that works too. Click and drag, double click. Either way is fine.
Like that.
That's it. Yep, that does the trick. And you can change that title at some point to make sure that it shows that. Well, we're also going to, that's fine, whatever. Well, getting technical. Your masses are in grams, newtons are in kilogram meters per second squared, not gram per meter squared. So your units are off. But there's a quick fix to that. Number one, that way to do that is if you go back into that E3 or E4 cell and put parentheses around that subtraction, then divide by 1,000. It'll convert it to grams or to kilograms. All right.
Should I do the same with the first two columns here?
You can,
Or
if you do that with the first two columns, you need to take the 1,000 out of that one. Basically, I want you to be able to see first, identify that distinction, and number two is to get a slope that is actually in newtons. All right, so you got 216.7 newtons based off of this, which is a higher slope. Now you and I can clearly see that you've got that one data that's a little out of alignment. So for your case, we're going to add a second subset that does not include that to see what it would say if that one was in line with everything else. So let's right click again and add select data. And then add, call this subset. X values include runs 1 through 5, but not 6 for A versus, remember the horizontal versus A's. And then we're going to do the same thing with the forces, excluding that one there. Remember, you'll want to change that so that it stands out on a black and white printout. So click OK. I'm going to change the marker, but we'll do that. Let's do that now, just as a reminder. Right click on one of your data points. This is for, again, for other folks who avoid the trend line.
yeah.
There you go. And for my data series.
Data series.
All right, go to the paint bucket. Marker. Marker options. And then built in. Now you can either change the shape, which is fine. Go ahead. And then make it a little bit bigger. 6, 7, something like that. That'll do. That's good. That'll work.
Sure.
All right, and then let's go to right click again on one of those lit up data points. You find that if you kind of go a little bit on the edge of the data point, then it's easier to get the data point and not the.
Oh,
So if you go up to that next to the last one, look at 4 meters per second, not that one, the last orange one. Go down,
this,
drop down a little bit below that trend line. So you're wait for the little tag to change. There you go. Now you can right click and add trend line.
gotcha.
Little tricks that you pick up over the way.
Yeah.
All right, and then we need to go down there, add the equation and intercept and y r squared rather.
Yeah.
Now your value is 209.1 grams, so that one is clearly pulling it up, making it a bigger problem. So move that one down just below that equation down below so that you can have both of those on there. So in your conversation, you'll be saying, with the full data set of range that we measured, 216.7 grams. But if we remove the one that is clearly somehow off, then we get 99.9. 99 you got a better R squared, and your mass is measured as 209.1 grams. So,
Yeah.
okay. So now your mass, when you measured on the scale, how much was it?
It was
201.
201.05 grams. Yeah.
Okay, so if you compare that with 209, you're probably going to get right around 5 to 8% error, which could be explained with a few different things, but it's still increasingly higher, saying that you moved more mass than you actually, at least that you measured on the scale. And the question then becomes, did any other parts of the system move when you were when you were dropping the masses? And if it did, what was it?
There have been like the pulley.
Yes, the pulley. And the pulley is 5 grams of mass. So that accounts for 5 grams of the overage.
I see.
And then the next thing is it could be friction. It could be some other factor that we're not sure yet. We're going to take a look at that with part C. So now you can explain that. So why don't you go down there, bro, at S2 and just put pulley mass is 5 grams. Just making a note to yourself, really. All right. So now we're going to do pretty much the same thing for part C. Now here's the catch. When you come up with data that you're not entirely confident about the relationship between the two, the best thing you can always do is just put those two variables against each other on a plot and see what the relationship looks like. If it looks like what you expect it to, then you can clean up your graph to do that particular relationship. But right now, all you know is that Dr. T told you guys to do an inverse mass. And the only reason you see that is because when we rewrite F equals ma, we get acceleration is force divided by mass. So we're going to check to see if that relationship holds true. It seems like it does in the first one, so we're feeling pretty good about it, but we're going to make sure. So let's make a new graph. Right click on highlight your accelerations in this case. We're going to do the same thing we did before. Insert a XY plot, and then we're going to go in there and add. And then go up to your ribbon and click on select data. All right, edit. And then the X values are going to be just the masses of the system, total mass of the system. Click OK. And OK. And then let's go up to quick layout. All right, you can see that as a linear fit, it seems like it's pretty linear. But if you look at the actual data points, except for that last one, which we already identified as being problematic, you seem to have some kind of a curve going. So let's ask Accel to do something about that curve. Click on the actual trend line, and you'll notice your side panel will pull that up. If your side panel is not up, you would just right-click and go to Format Trend Line, but that's here you are now. So go ahead and go over to the options there. It's linear. Let's change it to a power law. Not polynomial, power.
Power. Oh, okay.
And so if you look at the formula that it gave you, it says your formula is 0.0951 is the coefficient, and your x to the something power, in this case, this is your mass to the negative 1.01 power. So now you know for sure that this is an inverse relationship between acceleration and mass, because x is to the negative 1 power.
Mm-hmm.
Now, what you want to do is we can do one of two things. And what we're going to walk through is the simplest way to do this, which is to just change the data on the same graph and be quick on that. The other thing is to copy this thing and then just change the data for that one. And they're both the same thing. One just keeps and retains this 1 over m relationship. Right click on your data and select data. It doesn't have to be the exact data. The nice thing about the chart is that it'll give you select data for anywhere you click. So right click, edit, and then change your L4 to L9 to O4 to O9. And then highlight column O data. There you go, enter, and okay. There's your data. Now it looks like that. So we need to change it back to linear. So click on linear over in your side panel. This is the slope of acceleration versus inverse mass. From the relationship of Newton's second law, that means that's the total force that's accelerating this system. Remember, you added masses and you kept the same difference of mass, which was the 10 grams, to be what causes the full system to accelerate, including the pulley. Okay? So this says 0.0971 is your force. So take that value, go to a cell somewhere, if you will, some other cell right off to the side. Yeah, that's fine. And put equals 0.0971 divided by 9.8. And then enter. Now equals, in that space right there, just put equals and click on the previous cell times, times 1,000. 9.9 grams. This is accounting for nearly everything that you have on your system, 9.9 grams, because remember, you took off the calibrating mass, so that's no longer a factor there. And so it's 9.9 grams that's causing the system to accelerate.
Okay.
That make sense?
Yeah.
So you did take the calibrating mass off, yes?
Yeah.
Okay.
Yeah. Yeah.
Okay. if your data is a little bit sketchy because it looks so good, here's why. We expect there to be force. Remember, we made those slopes for A. You said you had to add 3 grams of calibrating mass on there. So we should be seeing in this force 3 grams worth of friction, which would be opposing the acceleration of the system, or the total acceleration due to gravity 10 times 9.8. So we're seeing that not being subtracted off here. I'm going to invite you to think about some explanations for that. Why is it not being picked up here if it was being picked up before? Was your technique right or wrong during part A? Part B looks fairly consistent, but again, in that case, you have that one last bit, which may have been just a matter of moving a 5 or 2 gram incorrectly from one to the other. and then running that system. So there's a couple different explanations for that, but I don't know that friction is going to be an explanation for that. Well, it might be because it says 209 grams. Which mass did you put the calibrating mass on?
Is mass 1.
With the 100 gram?
Yeah.
Okay. So, so your tables that are needed for the report are going to compare the mass from slope B compared to the total mass you had on there, 201 grams, 0.05. And then for part C, comparing that either the force resist, you calculate the force resist and then do that and compare, or you can compare 9.9 grams of reported force or mass that's being accelerated to help accelerate the system compared to 10 grams. But then when you're in the analysis section, it's important that you talk about, okay, we expected 1 grams worth of this, which means that should be closer to 6.7 or something like 6 or 7 uh, grams total, because those other 3 grams would be friction that's taking away from the acceleration of the system.
I now that I'm thinking about it, I don't think we took off the additional calibration mass in
I
part.
see.
Yeah.
For part C, there's your explanation. So what you're doing now is you're seeing from the data the results, not only what your experimental operation was, but also you can see the errors coming out a little bit more clearly. You can explain the discrepancies that you would expect in there. And that's what you're doing with these three. That's what you're doing with the graph now is to take it and say, in lab one, we got data and we want to compare that to 9.8. And we figured out how to do that and how to use Excel to do that. In lab two, we had motion. And in that motion, we saw, okay, I need to learn how to read the graph and know that this part is constant velocity and this part is constant acceleration, constant velocity, and so on. And then you extracted information and compared those from the different
Yeah.
graphs. Now we're doing that, but now we're a couple layers separated from the original data that we took, because your original data is just dropping them, watching them accelerate. What did you
Yeah.
capture? You captured the masses and you captured the accelerations and use that to build these tables. Now you have the graphs that come from the tables, and those graphs have a slope. This
Mhm.
slope for this data set is mass. This slope for this data set is force that's accelerating the system. And now you can say something about these results specifically that goes back to the physical experimental setup. Was there only 201 grams, or did we forget something? Aha, the pulley was moving. Aha, friction may have been another factor. For part C, you say, okay, well, is it friction? We get this number that's really close to 10, and you go, wait a second, maybe we didn't. Now you consult with James, and you guys come together and you say, you know what, we're in agreement. We didn't take the mass off for part C. So next time we need to make sure we're following the instructions better. And also we are able to explain it here, because we would expect there to be that force resistance would be more of a factor in this result. Does that help clarify things for you?
Yes, that clears things up for me. For the percent difference and percent errors for these two different tables, what would I be comparing? Would it just be these two, the M1 and M2 columns?
Oh, no. Okay. So for part B, you're comparing to the total mass of the system that you expect it to. You expect it to be, we're fundamentally expecting it to be 200 grams.
Yeah,
Physically, we know there's well, you said that there was three grams added on there, but your total mass of the system says 2.01 grams, which is 1 gram plus about half a gram for the strain. When you are preparing your tables for Lab 5, this is the ultimate detail to check to see what your results were. So I'm going to continue to use Joel's results. And you can see here, table 1 has his 216.7, the first slope, which has all 5 data points, and then 0.209 or 209 grams from the second slope, which is that truncated data. And they have the scale value of 201.05 grams, also converted, as you can see, written here in kilograms. The error is calculated for each of these using the formula that you see in the bar. If you're still not comfortable using formulas in Excel, let me know. Let's get you that skill set. The mass difference is going to be simply the subtraction of these two values, the mass, the experimental mass, and the scale measured mass, or for the purposes of this experiment, your accepted mass. And you see that works out once you convert that to grams to about 15.7 grams for the total set of data, or for just the subset, which seems to be more reliable, is only 8.5 grams, 8.05 grams, 8.05 grams. You'll notice that I've got a table marked with the Roman numerals, and I've got a little remark up here. This is just to kind of let you guys see this. Remember that you'll want to put that stuff into your Word document and make sure you keep your table title and label with the actual table itself. You'll notice that there's no units within the content of the table except for at the headers. Subscripting is employed, so if you again are still not sure how to use that, make sure that you reach out and ask for some assistance. A couple other things that we want to do to just kind of clean up the details here. The values in the masses here are given based off of their exact measured values. And we could technically take an extra data point, I think, from the slopes if we wanted to, but I'm not worried about that at the moment. But your error, you'll notice it's got a jillion extra decimal places. So you'll go up to the top again and you'll truncate your list with the little zeros and the arrow right there under the number subset in your ribbon. For those of you who don't know, that's called a ribbon. We'll keep it 2 decimal places, that's fine. Mass difference is fine, and this is fine. But another thing that you could do is, if you'll notice, I'm just kind of navigating here. I'm just going to hit the center line, and now these are all nice and organized, central to each column set of data, and makes it a little bit nicer to read, a little bit more consistent read. Table 2, by comparison. So the way that the system calculates, or the manual shows it, is that you get the slope from the graph that you produce, and then you subtract the resistance force, or you subtract you rearrange the equation that's in the lab manual so that you can obtain the resistance force, which should be on the order of a gram or 2, and then you divide by 9.8 to get your resistance mass and compare that to the offset mass, or the calibration mass as I was calling it in person. So this is the 1 gram that we expected. Some of you put 2 grams on there, some of you use no grams. But if you did have an offset mass, that's what will go there, and then you compare by percent error. Again, truncate your decimal places. We can probably go to 1 decimal place now for such a big error. And in this case, it's going to be a big error because he did not remove that calibration mass whenever they moved on to part C. But the mass difference here is almost 1 gram, and that should be, again, corresponding to the mass that you would put on there. Now, another way to think about this is to simply say, okay, I've got the slope from I'm going to just do this down here just a little bit. The slope is 0.0971, and if we divide that by 9.8 and equals that divided by 9.81, we get a number. This is going to be the mass in kilograms of the force that is the effective force that's moving the system along. And so then you go, all right, well, what does that mean? Well, if you take your subtract or let's convert that to grams. So that's just simply multiplying this times 1,000. And let's truncate that number because it's a lot to look at. So about 9.9 grams is what in his numbers would be. Yours may be closer to 8.5, 8.0, what have you. But this is the number he got. Again, they did not take that off. And then if you subtract the absolute difference from this 1 gram, then, or let's see here, that's the force. So then you say, whatever friction you would expect it to be, maybe, would be equal to 10 grams minus this value, because you expect it to be 10 grams to move the system. And the difference is going to be the friction, the amount of friction that's pushing the other way around. Most of you should be seeing about 1 point something grams. And remember that your slope from part A was not necessarily perfectly horizontal, so there was still some unbalanced friction that was playing a role in the system, and that would account for any parts of a whole gram that you were probably seeing in there. So I just wanted to kind of cover this and make sure that you saw these tables talked about as you are wrapping things up for this. If you need a little extra time because you're trying to make sure you understand what's going on here, send me an email. I will give you the extra time on this one. I want to make sure that you guys come away with an understanding of the system and Newton's second law. That's it. All right. Thanks for listening.